All right, hello gang, and welcome back to our weekly live stream. Today we're going to be moving on to a new chapter, which is optics, or sometimes called geometric optics. And it follows from what we did last week, where we spent a bunch of time talking about EM waves and learning that light is an EM wave. So it's made of an electric field and a magnetic field that are in sync and that oscillate as the wave propagates. And that, of course, is an important thing to keep in mind when it comes to light. It is an EM wave. But if we're going to study the behavior of light, we're actually going to do it in two separate parts. First part is going to be optics, what we're doing today. We're going to ignore the wave-like nature of light altogether. So yes, we will acknowledge that light is an EM wave, but we are not going to need to know anything about that to talk about optics today. Okay, we're going to treat light as if it propagates along a ray, so basically geometrically a line with a direction, and we're going to see how light reflects off of certain surfaces, how it behaves if you go from one medium to another, and how you can predict where mirrors and lenses are going to produce images for you to see. And none of that requires remembering that light is an EM wave. But then next week, we're going to go over interference and diffraction, and that very much depends on light being an EM wave, and so we'll zoom back in on that part of light and that property of light and see what the consequences are there. But there's an entire chapter of optics to be covered where we don't need to know that. Okay, so that's going to be the focus of today. I'm going to try to do as brief of a summary as possible because a lot of this has already been done in lecture, and a lot of it is just pure memorization. So optics is not very difficult to follow, to understand. There's only so many properties, and if you know them, usually you're able to do the ray tracing. You're able to apply the lens equation, the mirror equation, find magnification, things like that. But I am going to do a quick recap so that when we dive into problems, it actually, it's not completely new in case you're not up to date on the content. So that's going to be the plan. We'll start with like Snell's law and the law of reflection, and then we'll move to first spherical mirrors and then thin lenses. And so for those of you who are new, welcome to this live stream and this channel. I live stream every week, and you can find all of this content, the videos, the problems that I solve, along with homework with solutions at psychedemia.com. So feel free to check it out. If you go to the study guides page and you scroll to the bottom, you will find a Physics 8B live stream course, which is free for you to enroll in and has everything that comes with this live stream. So let's start by, in fact, talking about the index of refraction, which is something that we very briefly mentioned last week, but that we need to define. Okay, so the index of refraction, now this is going to be in the case of a transparent medium. Okay, now a transparent medium is a medium through which light can propagate. So for example, glass or plastic, water, air, I guess, is a medium, but theoretically we kind of, make equivalent vacuum and air, at least for the speed of light anyway. So a medium through which light can propagate is a transparent medium, and it's going to have what's called an index of refraction. The index of refraction is little n, and it is the speed of light, c, divided by v, the speed of light in the medium. Okay, so where v is the speed of light in the medium with index n. Okay, so n is going to have a value that, by the way, is always going to be bigger than 1 because v will always be less than c. The smallest n can be is the case for air is 1 because v is equal to c in air. So n air is equal to 1, and water is 1.33, for instance. Glass or plastic is around 1.5 or so, but the value is specific to the medium. And so you can actually identify a medium if you know its index of refraction. But what it does is that it measures how the light slows and bends or turns when it enters this medium. Now we'll see what that means when we talk about Snell's law in a second. But it is a property of transparent media, and for a given transparent medium, you have a given n. Okay. So then let's talk about the law of reflection and Snell's law. And we'll do that in the context of something that hopefully is relatable, at least to a degree. Let's imagine, a body of water, maybe a lake. Okay, something like that. And water has a certain index of refraction. It's 1.33 or 4/3. And air has, of course, an index of refraction of 1. Now, all I really care, though, is that here N2 is greater than N1. I don't necessarily want to make it about air and water. It's just that example is relatable, so I tend to use it. Okay? And what we're going to have is light coming in like this at a certain angle. And as long as it propagates in air, the ray of light will travel in a straight line. But when it enters water, it's going to slow down. Typically, light slows down when it enters a transparent medium, and it's actually going to turn. In other words, it's going to change the direction in which it propagates. Now, to quantify all of this, we're going to need what's called the normal. Okay, that's the direction perpendicular to the surface. And all our angles are going to be measured relative to this normal. So if I call this theta 1, then here I'm going to have a ray of light, and two things are going to happen to this ray of light. Some of this light will be reflected off the surface of the water, something you're probably familiar with. Okay, so this is going to be called the incident ray, and this is the reflected ray. And the law of reflection tells me that theta sub big R, the reflected angle, is going to be the same as the incident angle. Okay, so the law of reflection says that theta 1 is equal to theta R, which is theta reflected. So that's the law of reflection. Very straightforward. And the reflected light is going to be contained within what's called the plane of incidence. Okay, so the plane of incidence is the plane defined by the incident ray and the normal. And so in this case, it's the plane of the sheet of paper or of the screen. And what we're saying is that the reflected ray will also lie in that plane. So it doesn't start coming out of the page or going into the page. It remains within what's called the plane of incidence. That's the plane defined by these two directions. Okay? Now that is just reflection. Now there will always be reflection. Okay? Most of the time, not always, there will be refraction. Okay, we'll talk about when that might not happen after. Refraction is different. Refraction is some of the light is going to enter the water. And as it enters the water, it slows and it bends. The direction bends, in fact, toward the normal, defining an angle theta 2 that's smaller than theta 1. And this always happens. If you go from low index of refraction to high index of refraction, light will slow and bend toward the normal. In fact, you could argue that then if you do the opposite, if you shine light, a laser beam, for example, from here out, then it will bend away. Okay? So if you go from high end to low end, as you exit, you speed up and you bend away. So this is called the refracted ray. And the direction of the refracted ray is given by theta 2, and theta 2 is given by Snell's law. Snell's law says that n1 sine theta 1 is equal to n2 sine theta 2. All right, this is Snell's law. And the same, the refracted ray is within the plane of incidence. In other words, it's within the plane defined by these two directions. It doesn't start coming out of the page or going into the page. All the rays remain within the plane of the screen here or the sheet of paper. Okay. So these are pretty straightforward laws. I mean, the law of reflection, there's nothing to it. It's theta 1 is equal to theta r, although it is surprisingly useful given how simple it is. And Snell's law is just, okay, n1 sine theta 1 is n2 sine theta 2. Usually you know n1 and n2, and probably you know theta 1, and you can therefore get theta 2. But of course, as long as you know 3 out of the 4, you can solve for the fourth unknown. So that's what happens when light hits water. Okay, and because, and this is to prepare what comes next, because light will bend toward the normal when it goes into water, in other words, into a medium with a higher index of refraction, I can make theta 1 as big as I can possibly make it, which is like 89.9999999 degrees. Well, what's going to happen is that the ray of light is going to bend toward the normal. So yeah, you'll have a bigger theta 2 than before, but light will enter. So if you're swimming underwater in a lake, there is nowhere you can swim to hide from the sunlight if the sun is above. Okay? Light will always enter the water. Now, however, it's not always true if you go the other way around. So I'm going to borrow this, make a copy here. Actually, we'll go down here to have some room. And let's talk about total internal reflection. Now this is a really important property because it's what tends to be on exams, since it's at least a little bit more interesting than just plugging and chugging n1 sine theta 1 is n2 sine theta 2. Okay, so let's draw the normal to the surface just to have it. Okay, let's put it here maybe. All right, and let's draw a ray of light that this time comes from here. Okay, maybe you shine a laser, you're underwater, you shine a laser out, or something like that. Or there's an object, right? There's a big shiny fish right here, and you see the light coming off the fish. Okay? Whatever the case may be, this light, as it travels, hits the interface between air and water, and because n1 is smaller than n2, it will bend away from the normal as it exits, and it will speed up, but geometrically anyway, it's going to bend away. Okay. Now at some point, you can increase this angle, right? But you cannot go further than what's called a critical angle. Because whatever this angle is, this angle here will be bigger than this angle. And so as you increase theta, at some point you hit theta critical, and that's the point where your refracted ray is at 90 degrees from the normal. It has bent as far away from the normal as it can. But you haven't made it to 90 here, right? You're not shining light like this. You have a certain angle theta critical. But because this ray, the refracted ray, bends away, then that is going to hit this angle here, theta, is going to hit 90 before theta critical hits 90. Okay, so this is the limit between having refraction, and you could argue you kind of have a refracted ray, right? It's at 89.99999 degrees from the normal, but okay, it's still there. It's still, light still enters air. But if you were to make your angle any bigger, right? If you were to choose an angle theta greater than
theta critical, you would find that since this cannot bend away from the normal further than 90, then you no longer have a refracted ray. The light undergoes total reflection at the interface. Okay, so this is what's called total internal reflection. Light remains trapped in the water and does not escape into the air. Which means that if you're swimming in a lake, like we said before, there is nowhere you can swim to where the sunlight doesn't enter the water. However, conversely, if you are underwater, there's somewhere you can swim to so that someone cannot see you anymore. Right? If you imagine that there's a shoreline here, okay, and you're standing here, maybe you're fishing or something, then there's somewhere that the fish can swim to so that the light that it emits never reaches you. Right? And so, in fact, the bigger this angle is, the more likely that's going to be the case. And so that's why we say there's something lurking under the surface, right? If you get right under the surface, this angle is going to be very big. You're not going to be able to see what is just under the surface there. Okay. Whereas if the fish were swimming somewhere down here, then okay, you know, light would do this and would bend away and you would see something like that probably. Right. So it's an interesting property. It's something to keep in mind. And you want to be able to find theta critical. Okay, but this only happens if you go from N2 greater than N1 to N1, that is low, smaller. So only occurs when light goes from high N to low N. Okay, but it's not every time. Like sometimes, you know, if, for example, if you had an angle that is smaller than theta critical, then like we drew before, yeah, light will exit. Okay, so I should say this is not a correct statement. So I would say if theta is greater than theta critical. The point that I was trying to make is that don't look for total internal reflection if you're going from low N to high N. It's never going to happen. The requirement is that you go from high N to low N, and then of course your angle has to be greater than theta critical. Now how can you find theta critical? Well, you would say that N2 sine of theta 2 is equal to N1 sine of 90. Sine of 90 is 1 for that matter. Okay, now I'm going to leave it like that. If I have air here, then I would know that N1 is equal to 1, but it doesn't have to be the case. Okay, so to be general, I'll just call it N1. We just agree that N1 is less than N2. That's all. Okay. So these are two laws, the law of reflection, the law of refraction, with the special case within the law of refraction, or Snell's law, that is total internal reflection. And there's a whole bunch of problems in optics that just involve these laws. There's a lot of fun things that we can study and think about that don't require more than these laws, which are typically pretty straightforward to apply. The worst case is you have to figure out some geometry based on the problem, but it's not even, that doesn't make the law hard to apply. It's just a separate geometric consideration that you have to deal with. So my point is, there's a lot of problems that just involve these two laws. They tend to be pretty straightforward, and there's not much more we can say about the law of reflection and Snell's law. Now, it is important that we know that they exist, however, because then we can start being creative and we can shape certain objects to have certain properties. Maybe they're shiny and they reflect light, or maybe they have a certain shape and then they're transparent and they let light through. So the first case would be a mirror, and the second would be a lens. And if we understand how reflection and refraction work, we can predict what will happen to light as it strikes the surface of a mirror or it goes through a lens. And that's what we're going to try to do here. So again, I'm not going to go in full-blown detail. This is going to be a summary. But we'll start by studying spherical mirrors, and then we'll do a problem to see how to apply all of this, and then we'll
talk about lenses, and we'll actually do a problem that mixes both the mirror and the lens. Okay, so a spherical mirror is a piece of a sphere. You can think of a Christmas ornament, and you can take a slice of this Christmas ornament, right? And so you have something that kind of looks like this, right? It's like, that's the slice that you cut off. And the question then is, do you make the inside shiny? That's a concave mirror. Or the outside shiny? That's a convex mirror, okay? And so I'm going to draw the two cases here side by side. Now what you're going to see, more likely than not, is people draw concave mirrors like this and convex mirrors like this. Maybe they do this to indicate the back of the mirror. Okay. And in truth, yes, okay, you know, we should be drawing a piece of a circle to represent the fact that these are spherical mirrors and we sliced off a piece of a sphere. The problem is, on average, we're pretty bad at drawing a slice of a circle, as evidenced in my very poor drawing here. So even though, yes, that is truly the shape that these mirrors have, we're going to use a symbol that's far more accurate and way better for ray tracing, which is going to be the following. Okay. If I tilt the edges inward, what I'm saying is that I have a mirror like this, where the back of the mirror is here, okay, and the shiny surface is this surface here. Okay, this is a concave mirror. On the other hand, if I draw the mirror like this, and I bend the edges back, and then I make this the back of the mirror, and this is the shiny part, well, this is a convex mirror. This bulges out toward you. Now these mirrors are going to behave differently. They're both going to reflect light, but they're not going to produce the same type of images. And so what we're going to do is define first the center of these mirrors. Okay, remember that these are pieces of spheres, right? So really you have, you know, one big sphere like that with a center around here. We just draw a piece of it, that's the mirror. But the concave mirror has a center on the same side as its shiny part, or shiny surface, whereas the convex mirror has a center that it's on the side opposite the shiny surface, the reflective surface. And in between the center of the mirror and the mirror itself, on the axis, we have what's called a focal point, F. And this focal point is going to be a certain distance, F, either in front of the concave mirror or behind the convex mirror. And because the distance from the center to the mirror is 1 radius, because it's a spherical mirror, we know that F is going to be half the radius. Now it's going to be plus r over 2 if you have a concave mirror. It is going to be minus r over 2 if you have a convex mirror. And of course the sign matters. Okay, so that, you know, the plus or minus is going to matter when it comes to the mirror equation. But the point is, one type of mirror has a positive focal length, the other one has a negative focal length. And one of them has a focal point, F, in front of the mirror, the other one behind the mirror. And so now, if we go ahead and we do some ray tracing, we can see how light behaves as it hits the reflective surface of these mirrors. So what we're going to do, I'm going to do ray tracing for 3 different rays. Usually you only need 2, so 3 is overkill. But I'll draw all 3 because, well, sometimes it's just easier to have options, and it's not always the same 2 that are the best ones to draw necessarily. So
let's consider an object. Let's say a candle, because I think we can all agree that a candle emits light. Okay, now the truth is that all objects emit light. That's why you see them, right? Light comes off of me, reaches your eye. That's why you see me. Same way that is why I see you. Okay, so yes, I don't glow, right? I'm not a light bulb, but I'm a secondary source of light. Light from the sun or from light bulbs reflects off of me and then allows you to see me. That's how that works, okay? So you don't have to glow as an object to emit light. All things that you can see, the reason you can see them is because they emit light, and the light reaches your eye. So, but let's take a candle, because like that, usually nobody argues against the candle. It's an object and it emits light, so perfect. It's a primary source of light. At least the flame is. Okay, so we'll do some more ray tracing later, but let's just learn the basics of ray tracing. Concave mirrors are a little trickier because there's 3 possibilities depending on how far you put the candle from the mirror. Convex mirrors are great. There's only one outcome. It's always the same. Doesn't matter how far the candle is. So I'll draw one of the scenarios for the concave mirror, but the rules will always be the same for the rays that I'm going to draw. So we are going to draw what are called principal rays. Those are rays for which I know what happens to them when they hit the mirror. Okay, so the candle, of course, is going to send light in all directions, but I'm not necessarily sure what happens to light that goes out in all directions. I only know what happens to certain rays. Those are what we call principal rays. So one of the principal rays is the ray that comes in parallel to the optical axis. By definition of the focal point, this ray of light reflects off the mirror through the focal point. Then there's going to be the ray of light that leaves the candle, hits right here, and well, by the law of reflection, I know that it's going to reflect at the same angle here as here. So I can draw that reflected ray. Okay. Let me just make it a smidge longer. Okay. So this is why I was saying that we typically don't need 3 rays, 2 are sufficient, because images form where emerging rays either intersect or appear to intersect. Here, these emerging rays, they're emerging because they leave the mirror, right? They emerge from the mirror, intersect here, and therefore my conclusion is that the candle is going to create an image down here. And light actually converges at this point. If you were to put a screen there, light would hit the screen. Therefore, you have a real image. Okay. Now there is a third ray. Let's just learn how to draw it so that we can have it, in our arsenal for later. There's the ray of light. Now this one always weirds everybody out, but bear with me. It's the ray of light that leaves the candle aligned with its center. But because, now you're like, well, it doesn't hit the mirror. It's like, no, I get it. Like it does, right? I didn't draw anything to scale. The mirror, yeah, think of it this way, right? The mirror is actually a piece of a sphere. And the thing is, if light leaves aligned with the center, that ray that I just drew is going to be a radius of this sphere. That means that, and again, it doesn't look like it, but it's going to hit the mirror at 90 degrees, and it's going to reflect along itself. So we never draw this part, right? We're like, no, yeah, okay, we're not going to do all that. That's too much. Like, that's overkill. We're just going to draw the ray that leaves the candle aligned with C, and we're just going to remember that it reflects along itself, and therefore comes down here, and, well, in theory, should converge here, but based on my drawing, it kind of doesn't. So that's the other problem. The problem that we have is that when you draw 2 rays and they intersect, fine. When you start to draw the third one, no guarantee that it behaves nicely and it exactly converges where you want it. So what I should have done is I should have cheated a little bit. I should have been like, well, I should have done this. I should have been, this is the ray of light that I want. And I mean, not far off from being actually accurate.
And if you proceed with care, however, in other words, if you purchase a ruler and you scale your drawing properly, ray tracing will be exact and all three rays will converge at the same point. But if you kind of, do it, in a hand-wavy manner and not being very careful, not being very rigorous, then your third ray might not exactly converge here. But the point is, we have three principal rays for concave mirrors. The ray parallel to the optical axis emerges through the focal point. The ray that hits the mirror on the optical axis bounces off with the same angle, and the ray through C is not deflected. Those are the rules. Now you can put the candle wherever you want, so long as you follow those rules, you will figure out where the image forms. Now, practice being a good idea anyway, but the point is, I'm not going to draw all three cases. I'm just going to say those, that is what it is. You have those three principal rays to work with. Typically, you choose two of them, and you find where the image forms. Okay, so that's for a concave mirror. And for a convex mirror, I'm going to have three principal rays as well. And in fact, they're going to be the same rays, as in I will start with the one that emerges parallel to the optical axis and hits the mirror. Now, it is going to reflect, but you can't say that, oh, it's going to go through F. That doesn't make sense. Light does not go through a mirror. Light bounces off a mirror. So what's going to happen is that it's going to bounce off the mirror like this along a direction that is aligned with the focal point. So it does not emerge through the focal point. It emerges aligned with the focal point. Then the ray of light that hits the mirror on the optical axis, nothing changes. That one just reflects according to the law of reflection, like this. And then there's the third ray, the one that is not going to go through C because light will not go through the mirror, but will be aligned with C, is going to hit the mirror here in such a way that it will reflect along itself. And images form where emerging rays either intersect or appear to intersect. And these rays do not actually intersect, but they appear to intersect right here. So I'm going to get an image that forms behind the mirror. Now, because light doesn't truly converge here, if I put a sheet of paper here, I don't see anything. So this is not a real image. I cannot form it on the screen. It is, in fact, what we call a virtual image. Now, you might say, well, that's all fine, but how do I see it if I can't form it on a screen? Well, you'd have to be looking at this thing like this. And then your brain is going to trick you. Your brain is going to say, well, if you see light, coming like this, you have no comprehension of what a mirror is and that, in fact, the candle's right here. You think, because you think light travels in a straight line, that it must have come from here. There must be, the source of light must be over there. And that is why light is hitting you the way it's hitting you. Okay? And so that is what we call a virtual image. And that's how you would see it. You'd have to look into the mirror like that to see the smaller image that is formed of the candle. Now, if this is not relatable, let's make it very relatable. When you drive a car and you look in your rearview mirrors, a rearview mirror is a convex mirror. That is why objects in mirror are closer than they appear, because you will see something that is actually smaller than the true size of the object, and therefore you will think that it's further, but it's not. Right? It's just convenient to have a convex mirror because it does not matter how far the candle is from the mirror. You will always see an upright image that is smaller that fits within your rearview mirror. So that's what it means to be a virtual image. Every time you look in the rearview mirror, you see a virtual image. You can't form it on the screen. It's just, there's nowhere that light actually truly converges, right? As opposed to here, if you put a sheet of paper, those rays of light are going to hit the sheet of paper, right? If this were actually light from a laser, a very powerful laser that you can use to cut stuff, and you put a sheet of paper there, the sheet of paper will catch fire because the laser actually hits it, right? Okay,
So that is for spherical mirrors. You have to know how to do the ray tracing. You have to know how to find f if you're given the radius, because that's the definition. Focal point is in between C and the mirror. And of course you have to assign the proper sign, plus or minus, based on whether you have a concave mirror or a convex mirror. And then there are two more equations for spherical mirrors, and we can move on to lenses. We're going to have the mirror equation, the mirror equation is going to say 1 over d object plus 1 over d image is 1 over the focal length. This is the relationship between the object distance, the focal length, and the image distance. In other words, where the image will be produced. And then we have also magnification. Magnification is the ratio of the height of the image to the height of the object. That seems to make a lot of sense. And we can prove from geometry that it's also minus d image over d object. So that is magnification, and that is the mirror equation. And we'll see how to apply it. It's not that hard at all. The only thing we have to keep in mind when it comes to mirrors is that if d image is positive, the image forms in front of the mirror. If d image is negative, the image forms behind the mirror. Okay, that is a very important distinction, because the only difference we're going to see in terms of formulas, right, the mirror equation and magnification, between mirrors and lenses basically. So mirrors will have mirror equation and magnification, and lenses will have the lens equation and magnification. You will see that those equations are the same. There's no difference. The only difference is d image positive or negative? Because if it's positive for a mirror, the image forms in front of a mirror. But if it's positive for a lens, it forms behind the lens. And that's the only difference between the two. So you have to be very careful in not only watching your signs, but interpreting the sign of your answer and what it means based on what you have. Do you have a mirror? Do you have a lens? Okay. All right. So that is for mirrors. Let's go over thin lenses, and then we can do a couple problems. All right, so thin lenses. Well, now let's see what I can do here. Let me see if we can somewhat accurately depict a thin lens. Okay, and I'm going to make it thin. Okay, so there are different variations. These are not the only two options, but I could have a lens that bulges out on both sides. That would be called a biconvex lens. This is typically a converging lens. And then I could have what's called a biconvex lens. Now those are a little bit harder to draw, but humor me here. All right, it would be something like that. That is a diverging lens. Okay, now it doesn't have to be biconvex or biconcave. You could have lenses that are shaped like this, right? Think contact lenses. So, fine, fair enough. We just don't go there. But we limit ourselves to either biconcave or biconvex. Okay. So this is biconvex, by the way. This is biconcave, just to be clear. Okay. Now, when it comes to lenses, yes, it is true that that is what lenses look like. If you were to pick one up, either a converging lens or a diverging lens, you would see that they have this shape. This shape is not very convenient because if you have to kind of draw this, by hand on a test, what you're going to do? You're going to draw something like that or something worse. It's not going to be very accurate. So as nice as these drawings are, we're going to give them up for symbols that are much more accurate when it comes to ray tracing. Okay, the converging lens will be a double arrow like this that is meant to remind us of the biconvex shape of the lens. And then the diverging lens is going to be drawn like this. That is meant to remind us of the biconcave shape of that lens. Okay, so those are going to be a lot more accurate when it comes to ray tracing. Now, just like the mirrors had a focal point, lenses also have a focal point. The thing about mirrors is that mirrors are unambiguous. Let's just go back to mirrors real quick. Like, where's the front of the mirror? Well, nobody's questioning where the front of the mirror is. Like, it's facing the shiny part, right? So if this is the shiny part, then the front of the mirror is all of this. If this is the shiny part, then the front of the mirror is all of this. Like, yeah, obviously. Like, what you going to do? Put an object here? Nothing's going to happen. Okay. So mirrors are very straightforward in that sense. They reflect light, so the front of the mirror is going to be, well, where the light comes from, because it has to hit the mirror to bounce off of it. Lenses are not so obvious, because lenses will let light through in both directions. So is this the front of the lens? Well, maybe if I put the candle here it is. But what if I put the candle here? Well, then that would be the front, right? Whereas the back of the mirror is always the back of the mirror. It's unambiguous. It's the side that doesn't have the reflective coating. So the point is, mirrors are very easy to figure out. You always know what's the front, what's the back. Lenses, it depends. And what does it depend on? It depends on the direction of incoming light. So if this is the direction of incoming light, then this is the front of the lens. Okay, so the front of the lens is always going to be the direction, or the side from which, wow, can't do two things at once. Incoming light will determine what side of the lens is the front of the lens. The front of the lens is the side that has the incoming light. So this will be the front, and this will be the back. Same thing here. This will be the front, and this will be the back. And if all of a sudden you start sending light from this direction, then it flips, right? This becomes the front, this becomes the back, okay? But let's assume we have light coming from left to right. Just like concave mirrors and convex mirrors, both have a focal point, but not on the same side of the mirror. The same is true of lenses. A lens will have a focal point F located behind it in the back of the mirror. That focal point is going to be one focal length little f behind the lens. F will be positive if it's a converging lens. Okay, so I'm going to do this actually. So converging lens, diverging lens. Converging lens, F is positive. But there's no formula for it. Typically you're given it or you solve for it. But I can't say it's r/2. There is no radius. This is not a piece of a sphere. This is just a lens. So there's no radius to be had, and there's no relationship between F and the radius. Now a diverging lens works differently. It's going to have a focal point in front of the lens. That focal point is going to be one focal length away from the lens. Now F is going to be negative is all. Okay, so that's the only difference as far as focal lengths go. And typically their focal lengths are given unless you're solving for them. Okay, so that's important. And typically everybody agrees on this. Now, what I'm about to say, it's not like people don't agree, they do agree. They just don't usually teach it because some people don't see the point. But if you can say, well, light can come from any direction. It could come from the left or it could come from the right. It will go through the lens. The lens is transparent. Okay, well, is it not the case that now if I shine light like this, I get another focal point here, right, on the other side, which is now the back of the lens? And the answer is yes, I do. So technically, one might say that a lens has two focal points, one on either side, right? It's just, I'm going to draw this one in green so that we understand that this one is the one you care about if light comes from the right. This one is the one you care about if light comes from the right. Okay, otherwise, we keep the one that we have here, sorry, for this case, and here for this case. Now, why am I talking about the two focal points? Well, first of all, it's interesting that the lens is not going to care where the light comes from one direction or the other. You're going to have the same focal length on either side. But that set aside, I need to talk about these two focal points so that I can draw the three principal rays that you need to know for lenses. Now let's maybe do this. Let's call this one F prime. Okay, it's the less important one. Okay, because if I'm going to focus on incoming light from the left, then F is really what I care about the most. But I should keep in mind that there is F prime right here. Okay. So now let's do ray tracing. Now, I'll draw a candle. Right, because again, we agree candle is going to emit light. And I'm going to put it in somewhere here, something like that. And I'm going to do ray tracing. And it turns out that for converging lenses, it's going to be like concave mirrors. There's three scenarios. There's more than one option, depending on how far from the lens the candle is. You're either going to get a bigger or a smaller image. It's going to be upright or flipped. It depends on the object distance. But the three principal rays that I'm going to draw are going to be the same in all three cases. And then for diverging lenses, well, you always get the same thing, so that's the beauty of diverging lenses. Okay, so let's now start with ray tracing, and we will draw the ray that comes in parallel to the optical axis. Light is going to go through the lens, not reflect off of it, and this ray is going to emerge through the focal point. Then there's going to be the ray of light that leaves the candle and goes through the center of the lens. That ray of light is not deflected. And same as before, images form where emerging rays either intersect or appear to intersect. Well, here they actually intersect here. Light truly converges at that point. This image you can form on the screen because the light is actually going to hit the screen. Okay, and so those are two principal rays. Technically you can do everything with those two, but let's learn about the third one because now and then the third one comes in really handy. So, the third one is the ray that, oops, hold on, let me redraw this guy. This is F prime. The third one is going to be the ray of light that leaves the candle through the focal point F prime, right, the other focal point. And that ray is going to emerge parallel to the optical axis. Okay, so again, here we go, the third ray. It's not perfect, right? I should cheat a little bit and do this. It's going to emerge parallel, and it's going to converge here, where the image forms. So that would be the third principal ray to know. And now and then it's a useful one to have in mind. Okay, so that's how you would do ray tracing with converging lenses. What about diverging lenses? Well, we're going to draw the same rays. It's going to be a little bit different because diverging lenses work differently, but it's going to be the same idea. So let's start with the ray of light. that arrives parallel to the optical axis. Now this is a lens, so light has to go through. It's not going to do this. Okay, let's not do that. That's not right. Light is going to go through, and it is not going to reflect and go through F. It is going to emerge from the lens in a direction that is aligned with F. Okay, so this is going to be a dotted ray because it's not that light comes from F at all. It's just that that's the direction along which the light bends as it leaves the diverging lens. Okay, that's why it's a diverging lens for that matter. It takes parallel rays and it fans them out. And so that's the first ray. The second ray is the ray through the center of the lens. That ray is not deflected. And then there's the third one. Now the third one is tricky. It's not going to go through F prime because it's going to hit the lens before it reaches F prime. So that's not going to work. But it is going to be aligned with F prime. This part is going to have to be a dotted ray because light is not going to go straight to F prime as it hits the lens. In fact, it's going to bend and leave parallel to the optical axis. And so then, as it emerges, it's going to converge right here, and this is where the image is going to form. Now, light doesn't actually truly converge at this point. Well, the only ray that actually does go through that point is the blue ray, but the other ones don't. So the rays still appear to converge at that point, and that is going to be a virtual image. All right. And so then just to wrap up, we have the lens equation, the same way that we have the mirror equation for spherical mirrors. We have the lens equation for thin lenses. 1 over d object plus 1 over d image is 1 over f. It's pretty remarkable. It's the exact same equation. And then we have magnification, which therefore is also going to be the exact same equation. But by definition, first of all, it's going to be the height of the image over the height of the object, and that's going to be minus d image over d object. So you have the same math in both cases, but like I said before, the only difference that you really have to pay attention to is the sign of the image distance. If d image is positive, the image forms behind the lens. If d image is negative, the image forms in front of the lens. And it's the opposite for mirrors. If your image distance is positive for a mirror, the image forms in front. But that's because intuitively that's what you expect. A mirror is going to reflect light, so you're like, oh, well, okay, the image ought to form in front. Whereas a lens, light goes through, so okay, the image formed behind it. So that is why an image distance is positive for a lens if the image forms behind the lens. Okay, so, I mean, that's quite a bit already. Is there more to this chapter than this? Not really, other than practice. I mean, as in you have to get good at writing the lens equation or the mirror equation, at tracking signs. You have to learn how to deal with multiple optics, right? Because it doesn't have to be that we just give you a lens and that's it. You'll go have fun. Maybe there's a lens and then a mirror, or maybe there's two lenses, one after the other. In that case, what do? But it's gonna rely on you knowing how to do ray tracing and knowing how to find image distance using the mirror equation or the lens equation and throwing magnification in there if need be. Okay, so let's continue on with problems now. We'll start with this one. This one is a huge classic, and it's a great problem to review Snell's law, internal reflection, and all of that.
So we have this ray of light that enters this prism that has a base angle of 30 degrees and an index of refraction √3. And then inside the prism, the ray is seen to travel horizontally, parallel to the base. And the first thing we want to figure out is which incoming light ray shown, A, B, C, or D, is correct. Okay. So let's start off with looking at what happens here. Before we do, let's just remind ourselves what we talked about earlier real quick, and you'll see why. Okay, we did this. We drew the normal to the surface, and then we drew a ray of light coming in. Oop, no. There we go. And we said, okay, well, if you enter a medium with a higher index of refraction, the light is going to bend toward the normal. Right? This angle here will be smaller than this angle here. Okay. So in order to decide which ray of incoming light is correct, let's first come here, perhaps I'll zoom in, and let's draw the normal to this interface. Right, or as best we can anyway, let's draw something that somewhat resembles the normal. Okay, that's not bad. Okay. Now, we need light to bend toward the normal as it enters. So we can rule out, right off the bat, without thinking, we can rule out B. B does not bend toward the normal. It was horizontal coming in, it remains horizontal, not possible, right? Light ray B is going to bend toward the normal. It's going to give you a ray that's going to look like this. But it's not going to remain horizontal. So it's not B. Okay. Now, probably not C either, because this angle is smaller than this one, so that doesn't seem to make much sense. So you might think, well, maybe, hey, maybe it's D. Like, this angle is bigger than this one. But then you might argue, well, okay, well, this one's bigger than this one too, so is it A or is it D? Okay, well, it's very important to understand the drawing that we have here, where the incident ray is in this quadrant. The refracted ray is in the quadrant opposite, not in the quadrant right here underneath. So it has to be the case that if I'm going to end up in this quadrant here, my incident ray of light had to come from this quadrant here. Therefore, this is my answer. It can't be C, it can't be D. So light came in along ray A and then hit the interface between the air and the prism and ended up traveling horizontally in the prism. Fair enough. And then it travels and it's going to now hit this side of the prism. And we want to figure out why no light emerges from side BC. And then if it doesn't emerge from through that side, where does light emerge from the prism if it does? Okay. So let's do ourselves a favor. Let's redraw this. Okay, something like that. And here's going to be our ray of light. It comes in horizontal. And we need the normal because in all cases, the angles that are relevant are defined with respect to the normal. Okay, so if this looks like about 90 degrees, then okay, we're good to go. Make it a dotted line for clarity, and then we can try to figure out what happens at this interface. Okay. Now, let's say I don't know. All I know is that, well, I'm probably going to leave the prism, and I'll bend away from the normal because I go from an index of refraction n, which is square root of 3 in the prism, to an index of refraction of 1, the index of refraction of air. So I go from high n to low n. I bend away from the normal. I expect this angle here, which I might call theta 1, to be smaller than theta 2. Okay? And of course, these angles are measured with respect to the normal. Now, I also have to keep in mind that, well, hold on, if I go from high n to low n, there's a risk that I undergo total internal reflection. And if I do, then no light will emerge from side BC. Okay, so, but the question then is, well, how do I know? Okay, well, let's figure it out. Let's say that this angle here is 30, because that's what we're told. That means that this angle here is 30. Okay, so now theta 1 is 60. Let's compute theta 2 using Snell's law. And if we run into a problem, we're going to say, well, it's probably because we have total internal reflection. So let's write Snell's law. Snell's law is going to look something like this. It's going to be n sine theta 1 is equal to n air sine theta 2. Okay, and I want theta 2. So n air is 1, so I just have sine theta 2 is equal to n sine theta 1. That is going to be square root of 3 times sine of 60, which is going to be, well, square root of 3 times root 3 over 2. So let's just be clear. It's going to be this, which is 3 halves. Okay. If you try to arc sine that with your calculator, you'll find that there's an error. This is impossible. Sine can never be greater than 1. So this doesn't work. If it doesn't work with Snell's law, what it's telling you is that actually theta 2 doesn't exist. If theta 2 doesn't exist, the refracted ray does not exist. So, you know, it's a good guess, but upon checking with the values that I have, I come to the conclusion that there is no refracted ray. And the light undergoes total internal reflection. So instead of having a refracted ray into air, we're going to have a reflected ray like this. Okay. By the way, now we're going to hit the base, and so question number 3 becomes relevant, which asks, well, at which angle does this ray emerge from the prism? Well, let's see. Maybe it emerges through the base. Maybe not. Maybe I get total internal reflection again. That'd be something. But let's find out, right? Okay, so let's zoom in just to see what we're talking about here. Okay. By the law of reflection, this angle is this angle. So this is 60. Okay, so this means that this angle here is going to be 30. Okay, and the angle that I want is this angle here. We call that theta 3. And if I'm going to draw a refracted ray, I'm going to say, well, I leave the prism, or maybe I don't, but let's imagine that I do. I bend away from the normal, and I'm going to find an angle theta 4, and what the problem is asking me to solve for is theta 4. So if I only knew theta 3, I could compute theta 4 with Snell's law. Maybe it works out, maybe it doesn't, but let's see. Okay, so this is 90 degrees because this is the normal, which means that if we look at it, and if we look at this triangle in particular, we're going to say that the sum of the angles in this triangle is 180. So it's going to be 30 plus 30 plus 90 plus theta 3 is equal to 180. That gives me theta 3 is 30 degrees. And now I'm going to apply Snell's law down here. I'm going to try to compute theta 4. And, well, if it fails, like in part 2, then I'm going to say, well,
total internal reflection again, and it's going to bounce off, you know, like this, and then what happens? Or, well, maybe it exits, and that theta 4 is the angle at which it exits. So we're going to write Snell's law again. We're going to have n sine theta 3 is equal to n air sine theta 4. Okay, so if you want theta 4, n air is equal to 1, so we have theta 4 is inverse sine of n sine theta 3. That's inverse sine of square root of 3. Sine of 30 is going to be 1/2. Okay, inverse sine of root 3 over 2, well that's fine. That's going to give me an angle that exists that is 60. Okay, so light is going to leave through the base of the prism at 60 degrees from the normal, which is the vertical, at the base of the prism. So not super hard, but like I was saying before, it might very well be the case that the hardest part of this is geometry. It's finding your angles and your distances and all that, not actually solving Snell's law or the law of reflection. But okay, good illustration, my bad, of total internal reflection on a surface, but then on the other surface, you know, you hit it with the right conditions to get a refracted ray through the base. All right. So that was for Snell's law and total internal reflection. Now, we could do many more of those, but you'll find that they tend to be quite similar, and there's not that much meat on that bone. If we're going to, and I'm not saying it's not on exams, like some problems will just have Snell's law on exams, and you know, multiple interfaces in media probably, but it's just Snell's law, and you follow along and you solve. But more likely, if we want to make things a little bit challenging, we will design problems that involve mirrors and lenses, and perhaps at the same time, or perhaps multiple lenses, like an afocal telescope, which is also a classic. So with that in mind, let's do this problem here so we can kind of understand how to think through something like this, because it's easy to be overwhelmed and to not know what to do, or to try to do a bunch of stuff that just doesn't make sense and go around in circles. So you have a 4 centimeter tall candle that we place at x equals 40 centimeters. The candle is exactly in between a converging lens and a concave mirror. The converging lens is at x equals 30, has a focal length of 20. The mirror is at x equals 50, and it has a radius of curvature, little r or big R, which is plus 40 centimeters. Plus makes sense. Well, actually, my bad. We don't know if it's a concave mirror. I jumped the gun. I said it's a concave mirror because I knew R is positive, which obviously that's how you know. But point is, a positive radius of curvature is associated with a concave mirror. A negative radius of curvature is associated with a convex mirror. Okay. So first, ray tracing. So using relatively accurate ray tracing, find any and all images of the candle formed by this quote-unquote optical instrument. Okay, well, let's see. How do we decide what happens with the light here? Because it seems like, well, maybe the lens plays a role, but probably the mirror does something too, and how many reflections and how many cases do I have to think about? All right, so here's how you think through this. Without doing any ray tracing, okay? Your candle is going to emit light in all directions, okay? Let's think through what happens to the light without worrying about ray tracing or anything. Just keeping in mind that mirrors reflect light and lenses let light through. So some of the light is going to leave the candle, go through the lens, never to return. That's one case, where the only device that matters is the lens, and it will produce one image of this candle. However, some of the light from the candle is going to go to the right, hit the mirror. Mirrors reflect light. Light will then go through the lens because lenses let light through, never to return. That's my second case. So the second case is that first, the mirror creates an image of the candle. That image becomes an object for the lens, and the lens forms the final image. So there are two cases and two different images that are formed in this problem. Okay, and that's what you have to decide at first. You have to figure out how many cases you're dealing with. Then you can do ray tracing if you're asked to, or you can just run with the lens equation or the mirror equation depending on what you're doing. Okay, so, well, let's go ahead and go through it. So let's do some ray tracing on this guy, and let's only consider the lens. Okay, we're doing the first case where the light just goes through the lens and forms the image. Right, so I'm going to draw the ray of light that is parallel to the optical axis and emerges through the focal point of the lens. And then I'm going to draw the ray of light that goes through the center of the lens and is not deflected. And I know that images form where emerging rays intersect or appear to intersect. Well, these rays will never intersect. They emerge from the lens, but they will never intersect. However, they appear to intersect over here. Oops. If I extend them as a dotted line, they appear to intersect right here, which means that my image is going to form right here. This is going to be a virtual image, okay, because light does not actually converge here. So I cannot form this image on a screen. It is a virtual image. But what's happening is that I'm looking at this thing with my eye, and if I see light angled like this, I'm going to come to the conclusion, because I think light travels in a straight line, that there must be something here creating these straight rays of light. My brain has no way of comprehending that this lens here just bent the direction of light from the candle. So I get a virtual image, but that's where it would form. Okay. Second case. Second case is going to be where first the mirror forms the image of the candle. That image will serve as an object for the lens, and we will then do ray tracing with that to figure out where the final image forms. So it's a two-step process. Let's start by drawing the image formed by the mirror. I'm going to draw the ray of light that is coming in parallel to the optical axis. The focal point of the mirror is right here at x equals 30, right? Because it has a radius of 40, right? So this is 10, 20, 30, well, no, what am I doing? It has a radius of 40. Let me not destroy my drawing here. This is 20, this is 20, okay? 20 centimeters, 20 centimeters. And that's going to be r over 2. So the focal point of the mirror is right here at the center of the lens. Okay, so fair enough. That's where the focal point of the mirror is. Now that I know that, I can draw the ray of light that comes in parallel to the optical axis, reflects off the mirror through the focal point. All right. And then I'm going to draw the other ray, draw whichever one I want, but perhaps I'm going to draw the ray through C, right? So there's going to be light that leaves the candle along this direction that is aligned with C. It will reflect off of the mirror and go through C Basically, it reflects along itself. Okay. Now, actually, let me be a smidge more accurate, because I should do this. I should have this ray. There, it should go through. Should go through right here where the red ray emerges. That's better. Okay. But the point is that it is aligned with C. It reflects along itself, and images form where emerging rays intersect or appear to intersect. Same as before, though. These rays here emerge from the mirror, but they will never intersect, not on this side of the mirror. Instead, they will give me the impression that they intersect over here. So they appear to intersect somewhere way over there. Okay, which would be right here. So they are going to form a virtual image right here of the candle. It's virtual because light doesn't actually converge at that point. And this is going to be a virtual image created by the mirror. Now what I'm going to do is I'm going to say that, well, this virtual image created by the mirror will now behave like an object for the lens, and I will do ray tracing with the lens. Okay, so light is going to propagate, it's going to bounce off the mirror and propagate back from right to left, and that makes sense. I'm going to get the ray of light that leaves here parallel to the optical axis, like this. This ray is going to emerge through, careful, the focal point of the lens. Okay, the focal length of the lens is 20 centimeters, which we have right here. So F sub L is the focal point of the lens, just to be clear. And this ray of light is going to come out through FL. Okay, and don't get confused. This ray of light, this ray of light here does not know about this guy. Like, don't start to have them intersect. We're not talking about the same thing. Right? This red ray came from the mirror. Now, I say that because you don't want to confuse the two, but then I'm about to say that I'm going to use that ray anyway, and so why? Okay, so we agree. These rays, these two guys, came from the mirror. That's how we found B prime. Fine. Now I want two rays that come from B prime, and I'm going to figure out where they intersect. There's this guy, and then, okay, well, there's the ray that leaves B prime and goes to the center of the lens. It just so happens to be the case on purpose that the center of the lens is the focal point of the mirror. So I'm going to draw the ray leaving B prime that's going to live on top of this initial red ray, but it truly comes from B prime, and is going to intersect right here with the ray that came from the lens. These two emerging rays truly intersect right here, so I'm going to get a real image, right? I could form this image on the screen if I want, and that is going to be A double prime, B double prime, if you want to call it that. Okay, this is going to be a real image. Okay, so if you place a screen here, you will get a real image. Okay, so state specifically which of your image locations you could place a screen at to actually detect the image of the candle, and explain why. So, placing a screen here will allow us to see the image because light actually converges at B prime, B double prime, I mean. Okay, but that's the only real image we've produced. This is a virtual image. Up here, this is also a virtual image. So you can put screens there all day, you're never going to see these images. However, A double prime, B double prime, yes, you will see that if you put a screen there. Okay. And so then using math for each actual screen image detection location you gave above, find the X location of the image and the height of the image, and state whether it's inverted, same orientation. Okay. So in theory, all we have to do here is redo this but with math.
and there shouldn't be anything more to it, which is actually correct. That's all we have to do. And we're going to start, we have to do carefully. We're going to start by the mirror, with the mirror. We're going to find the location of A prime, B prime, which is going to be, if this is, this is 60, this is 70, it's going to be somewhere around there. We'll see where exactly, but it's probably going to be far more accurate to do it with math than to do it with ray tracing. And then we'll try to find the location of A double prime, B double prime. Okay, but to do that, I'm going to make a copy of this just to have it in front of me. We just have to be very careful, because when we do things in sequence, which is the way to do it, we have to make sure that we find the right object distance for the lens after we form A prime, B prime. Okay, so not that hard, just you have to be very organized and very methodical. Okay, so let's start by finding the image formed by the mirror, because that's the first step. Okay, now I put my candle here at 40 and my mirror is at 50. So I have an object distance, d object, which is 10 centimeters. And I'm told that the mirror has a focal length, call it f sub m for mirror, of 20 centimeters. Okay, so I'm going to use the mirror equation. And I'm going to use the mirror equation to find the image distance. So I'm going to say that 1 over d object plus 1 over d image is equal to 1 over f mirror. Therefore, now if I want d image, I'm going to say 1 over d image is equal to 1 over f mirror minus 1 over d object. And therefore, if I play the common denominator game, I'm going to get a common denominator that's d object fm. This is going to be d object minus fm. Careful, don't forget to flip this. Okay, we want d image, not 1 over d image. So d object fm divided by d object minus fm. That is going to be 10 times 20 divided by 10 minus 20. Okay, well that gives us minus 20 centimeters. Okay, d image is negative. What does a negative image distance tell me? It always tells me that I have a virtual image. As soon as d image is negative, virtual image. But depending on whether I have a mirror or a lens, it tells me if it's behind or in front of the mirror or the lens. D image negative will always be behind the mirror. So we're going to say that A prime, B prime forms 20 centimeters behind the mirror at, well, it turns out at x is equal to 70 centimeters, because if you tell me that my mirror is at 50, then plus 20 is going to be 70. Okay, so A prime, B prime forms 20 centimeters behind the mirror at x equals 70 centimeters and is virtual. That's because the image distance is negative. So a negative image distance will always tell me that I have a virtual image. Okay, so that tells me the location of A prime, B prime. While we're at it, and this is just for later convenience, let's find the magnification. Okay, the magnification is going to be capital M is equal to, well, we said it's minus d image over d object. Okay, so that's going to be minus 20 over d object, which is 10. So that's going to be plus 2. Okay, magnification is equal to plus 2. The fact that it is plus tells me that the image has the same orientation as the object. That's true. The fact that it is 2 tells me that it's twice as big as the object. Well, relatively so, yeah, somewhat. My ray tracing isn't perfect, but it looks like that's a reasonable factor between the two, between the object size and the image size. Okay, so that's just the image formed by the mirror. Now, what I was saying earlier is that, let's make a copy of this and bring it down here. We have to be careful when we do these sequential optics things, like first the mirror, then the lens, that when we now work with the lens, we want the right object distance. Okay, so remember, this is my lens.
this is now the image from the mirror that behaves like an object to the lens. And so this is going to be my object distance. Okay, so d object, or whatever you want to call it. Okay, well, my lens is at 30, this is at 70, so this is 40 centimeters. Okay, so now I have to look at the image formed by the lens, and I have to say that my object distance, DO, is 40 centimeters, that's what we just found over there, and that the focal length of the lens is 20 centimeters. Okay, so now we apply the lens equation. Now, of course, the lens equation is the exact same thing mathematically as the mirror equation. So I'm going to have 1 over d object plus 1 over d image is equal to 1 over FL. Now, if I do the same solving as before, I'm going to find that d image is d object FL divided by d object minus FL. That's the same math. Okay, so I can go a little faster now because I've done the full derivation above. So this is 40 times 20 divided by 40 minus 20. Okay, and this is 40 centimeters. It is a positive image distance. What does that tell me? Well, a positive image distance always tells me that I have a real image. So I know that A double prime, B double prime is a real image. That's what I found with ray tracing. But it also tells me, because I have a lens, that the image forms 40 centimeters behind the lens. And careful, this is the front of the lens because that's where the light comes from. This is the back of the lens. Therefore, I form 40 centimeters to the left of the lens. If the lens is at 30, this is going to be x equals minus 10. And so we're going to say that A double prime, B double prime forms 40 centimeters behind the lens at x is equal to minus 10 centimeters and is real. All right, and so let's get the magnification while we're at it so that we can get the total magnification of the system. Okay, so magnification M, I should probably call it M2. Let me go call this M1 for convenience. M2 is going to be minus D image over D object. That is minus 40 divided by actually 40. So that is minus 1. So negative tells me that A double prime, B double prime is inverted compared to A prime, B prime. That's true. And that the object A prime, B prime and the image A double prime, B double prime have the same size. Which again, my ray tracing is not perfect, but seems like ish, reasonable. So, I found the final location of the image. The image is real. And perhaps I want to find how the image compares to the object, to the candle, not to A prime, B prime. Now, in which case, I need to find what's called the total magnification. Now, the total magnification of such a system is always the product of the individual magnifications. That's actually why I computed M1 and M2 in advance. So it's going to be M1 times M2. That's going to be 2 times minus 1 is equal to minus 2. And so the conclusion of finding a total magnification of minus 2 is that A double prime, B double prime is twice the size of the candle, which is going to be 8 centimeters, and is inverted compared to the candle.
So optics is very, I want to say straightforward because I can think of some problems that are a little tricky, but it's very systematic, right? It's very scripted in a way where you just have to be careful to identify object distance, image distance, focal length, plug that in properly into the mirror equation or the lens equation, compute magnification. We should know that total magnification is the product of the individual magnifications. That's useful. And the point is that as long as you are very organized and methodical, optics aren't so bad. Okay, but you have to make sure that you have to refer to the right distances in your equations, and more importantly, and this is the biggest pain point and usually the biggest source of errors when I grade exams, you have to make sure that you know the difference between positive and negative image distance when it comes to mirrors and lenses, okay? Because it turns out that everything that I did here, even though I did do it with the drawing because it helped, I could come to all the same conclusions that I came to with ray tracing just by looking at the sign of the image and the magnification, right? It would tell me if it's upright or inverted, bigger or smaller, real or virtual. I could tell just by doing the math, but therefore it matters, right? The image being positive means something, the image being negative means something else. Positive D image is real image, negative D image is virtual image, always, all the time. However, within that, positive D image does not mean the same thing for a mirror or for a lens. Positive D image, the image forms in front of the mirror and behind the lens. Negative D image, the image forms behind the mirror or in front of the lens. And you have to have that in mind and really have everything squared away. And then optics becomes very easy. But it's super easy to drop a sign or make a mistake, especially if you don't know these rules off the top of your head. And that's usually where students have the biggest trouble with optics, because otherwise the math is not what's going to challenge you. The ray tracing is usually not the problem. It's just knowing those conventions and those rules so that you know how to interpret the results that you get. So that was part one, if you will, of studying light. We went from discussing what it was as an EM wave last week to, for now, thinking of it in terms of rays. And again, this chapter, we call it optics, but sometimes you even call it geometric optics. It's all geometry. And it ignores fundamentally the wave-like behavior of light. But next week, we're going to do interference and diffraction, and so then we are going to have to consider light as a wave, and we're going to see that because it is a wave, it has certain properties that are inescapable, and some of these properties are, let's say, surprising, to say the least. In particular, interference and diffraction and things like that. So we'll talk about that next week, and that'll kind of put a nice bow on light. And the last live stream is going to be on quantum, which is kind of a checklist of different things. It's as bad as you want to make it, let's put it that way. So if the math stays reasonable, it's not terrible, but the math can go wild very quickly in quantum. Anyway, that's it for this week. As always, thank you for watching. I appreciate it. Best of luck with the final stretch. We're almost there. We're so close. If you can, do physics during Thanksgiving. I get it. Nobody wants to do physics. Certainly nobody wants to do physics during Thanksgiving. But it is, if you can, put some time away, it is a great time to just kind of sit down and go through quasi everything, really. I mean, by the time Thanksgiving rolls around, we've covered almost every single chapter of the course, maybe except the last one. And so it's a great moment to kind of just go back and, refresh before we come back, and the last 2-3 weeks are just, an insane race to the finals. Because it's going to go really quick, and there is a lot of material to conquer in 8B. So I know nobody wants to do physics during Thanksgiving, but if you can find some time, I think you'll thank yourself later, it might be worth it. Anyway, I'll be around for those of you who are in the masterclass, so don't worry, we can go over some stuff then. And for all the others that are watching the live stream, I will see you next week with interference and refraction. Have a great rest of your week. Best of luck with the end of the semester, and I will see you soon. Take care.